Hello everyone, this is Dia from Academy. In the previous video, the concept of dense set has been introduced, so now we will see the important property of the dense set, or the equivalence of the dense set to a property of the closure of a set. That is, if we know the closure of any set is equal to x, so the upper formality is if x and tau is a topological space and A is a subset of x, then the closure of that A is equal to the set x, then this is equivalent to the definition of the dense set. If we know that A closure is equal to x, then we can say that A is a dense set. And if we know that A is a dense set, then we can say that the closure of the dense set, or A, is equal to x. So we will prove this for both of the sides, for the necessity and the sufficiency as well. So now, taking the first side, so the given thing is that x and tau is a topological space, A is a subset of x and A is dense set, then we can prove that the closure of the set is equal to the set A. For proving this equality, we have to prove two things. The very first thing is that A closure is a subset of x, and the second thing is that x is a subset of A closure. In general, we know that if A is a subset of x, then the superset of A, that is A closure, is also a subset of x. Then this is generally true. So the only thing that we have to prove is that x is a subset of A closure. So this is our target right now. So by definition, we know that for all of the open elements of x or the members of tau other than empty set, intersection of A and U, also not empty, for the dense set. As x is also an open set, so we can replace U with only x here. That x intersection A is also not empty. So if A is any random element from x, so there are two possibilities, that A is in A intersection x, or A is not belong to A intersection x. So there are two possibilities here from by definition of the dense set, and A belong to x. So from this we can write as there are two possibilities in other way, that A belong to A or A belongs to A closure. So this is other way of writing the two possibilities, that A is a member of the set A or A is a member of this A closure. And we know that we understand this in this way. If this is the closure of the set A, then by definition of the closure of a set, we know that the set A is a subset of the closure of the set. So if A belongs to the set A, if A is right here, so this implies that A is also in the closure of the set. And if this, because there are OR condition in both of them, that's why there is a OR condition in both of them. And if it is not, A does not belong to A, but A is somewhere here, not in the A set, but in the A closure, then this is true. For both of the condition, eventually A is a part of the A closure. So what we have in the beginning, A was the element of x, and by applying the definition of the dense set, we know that A is also a member of A closure. So this whole thing implies that x is a subset of A closure, and we have proved that the dense set is equal to the set x, because combining of the two subset relations of x and A closure. So we have proved that if A is a dense set, then the closure of the set is equal to the set x. Now we will see that if we know that A closure is equal to the set x, then the set should be a dense set. So the given statement is x in tau topological space, A is a subset of x, and A closure is equal to x. And we have to prove is A is a dense set. So let's take an element from the set X. We know that relation of closure of the set and the accumulation point is that A closure is equal to A union A derived. So if A closure is equal to X and we pick a point A from the set X, so this implies that A is also a member of A closure. So A belongs to A closure, and this thing implies that A belongs to A union A derived set. And this thing implies that A is a part of the set A, or A is a part of the set A prime. So for each open set that contains the point A, so the intersection of the open set and the A should not be empty, because if A is a member of the set A or A is a member of the A derived, then we can talk about the open sets other than the empty sets in the topology. So this is true for all of the elements of the topology. And this is what the definition of the dense set, that intersection of every element of topology except empty set with set A should not be empty. Then the set A is dense set. So this is the definition of the dense set, and we have proved now that if A closure is equal to the set X, then the set is a dense set. So this is for now. If you're looking for more such videos, then you can subscribe this channel in order to watch more upcoming videos. We will meet in the next video. Till then, take care. Goodbye.